Hi friends. This week I am talking to a theoretical physicist. Bit of a departure from my usual sort of guests, but she's very interesting. Sabine Hossenfelder is a theoretical physicist, blogger, and author. Her most recent book, Lost in Math: How Beauty Leads Physics Astray, talks about physicists' obsession with beautiful theories and how this is potentially leading to a restriction in progress for physics overall. Now, it sounds like quite a nebulous and difficult to define area, and it turns out that it actually is. But we do a pretty good job of working out just what is happening in the physics world at the moment. What I found particularly interesting was discovering just how much politics influences physics. To get your research funded, what the hurdles are that you need to jump through, and whose rings you need to kiss in order to be supported. It seems very contradictory to think that a scientific subject area requires people to play a game akin to what you would presume in Wall Street, where you're sticking to the right kinds of rhetorics and you're pushing the correct narrative coming from the right educational background, coming from the right conceptual theoretical background. Really, really interesting. And it was a whole world that I didn't even know existed. So here we go. Sabine Hossenfelder, how are you today?
I'm doing fine. How are you?
Very good, thank you. Where are you in the world at the moment?
I'm in Heidelberg. That's like 100 kilometers south of Frankfurt.
Oh, very nice indeed. Very nice. So I want to get straight into it. You will be the first physicist which we've featured on the podcast. So the weight of the entire world of physics is resting on your shoulders at the moment. I want to ask a really fundamental question. It's been a really long time since we've seen major breakthroughs in physics, global newsworthy breakthroughs. Is there a reason why that's the case?
Well, one of the reasons is probably that you're reading the wrong news. There have been a lot of breakthroughs in physics. What I'm mostly concerned with are really the foundations of physics. So the biggest breakthroughs in physics are the ones that the Nobel Prizes are getting handed out for, and you find a list of that on the website of the Nobel Prize Academy. But I'm really talking about the foundations of physics. And there you are right. It has been a really long time since there has been a breakthrough where we have discovered something really new. I mean, the stuff that has made headlines, like say the direct detection of gravitational waves or neutrino masses, neutrino oscillation, and so on and so forth. These are all ideas that go back at least 30, 40, in some cases 100 years.
So this is physical proof of something which theoretically has been around for a little while?
Yes.
Okay. So is it a case at all that there's less stuff to discover, in quotation marks? Are we mapping so much of physics that the remaining dark spots on the map are limited? Or is it something to do with the approach that physicists have got at the moment? Or is there a sticking block or a glass ceiling that we've hit?
Well, that's a very good question, but how would I know? How would I know what is still left to discover? What I can tell you is that we have already discovered a lot, and that just means that the easy things have been done. The stuff that you can measure in your little laboratory with your handheld equipment and so on and so forth, that's all been done. That's the case in experiment. It's also the case in theory development. The easy things have been tried. So it's kind of natural to expect that it will become more difficult. Then on balance to that, though, we also now have a lot of more people working on it. So that should help, but apparently it doesn't. So we have, at least in the foundations of physics, we have had the mathematical structure of the theories that we're using right now since the mid-1970s.
Okay, so the low-hanging fruit, to one degree or another, as low-hanging as physics can get, I suppose, has been gathered to a large degree. Would you say that's fair?
Yeah, certainly.
Okay, so what is the current sticking point that we've got at the moment? Is it technological? Is it that the instrumentation that we're using? Is it the minds? As you say, there's more people than ever are dedicating their efforts towards physics. Are they looking in the wrong place?
Well, I do think that they are looking in the wrong place, but of course I don't know, I don't know what's the right thing to do. But the question that we can reasonably look at and try to answer is whether they are using good scientific methods that would give them the highest probability of making progress. And I think that's just currently not the case.
Okay, well, let's expand on that then. Why is that not the case?
Well, we have seen a lot of null results in the foundations of physics in the last 4 decades. For example, in the search for dark matter, this has been going on since the mid-1980s, that people have looked for the rare interaction of the hypothetical dark matter particles with normal matter. You can do this basically by building large tanks of some stuff, and then you put detectors around this stuff and try to measure these interactions. And people have tried, but they haven't seen anything. They have also looked for proton decay. That's a prediction of a certain new hypothesis. They have also, of course, looked for new particles in particle colliders. The most popular ones are probably supersymmetric partners of the already known particles, and that hasn't worked out either.
Is that coming out of the LHC?
Well, that's actually a long story. I mean, supersymmetry is an idea that also dates back to, the late 1960s or something.
Okay,
I'm not sure about the date, but people have, I'm not a historian, but people have looked for supersymmetry, for evidence of supersymmetry since at least the 1990s. And that didn't work out. Indeed, they should have seen it already in the 1990s. So they actually had data that was just in conflict with the idea that supersymmetry is obeyed by the laws of nature. And what they did was not to say, well, we've ruled out supersymmetry, but they said, well, we will just modify the theory. And so they added a new symmetry on top of it, which is called R parity. So now we have supersymmetric models that obey this additional symmetry called R parity, and that's compatible with observations so far.
Okay. So how long?
Okay.
How long do you pursue down a route of trying to find a physical manifestation that proves a theory before you actually say, well, maybe the theory's just wrong completely?
Well, you do it until you come up with something better. But that's the rub, because it's really, really hard right now to come up with something better, in the sense that you can get funding for it and collect sufficiently many people so that sufficiently many people agree it's better. And that the problem is you have a community like supersymmetry, which for the foundations of physics is a really, really large community. You have something like, 1,000 or 2,000 people of that order of magnitude. And if you try to say, well, maybe that's not the right path, that's really hard to get people to listen to. And accordingly, it's also hard to get funding for it.
Yeah, I can imagine. So how much of physics is about physics and how much of physics is about politics?
There is unfortunately a lot of politics, not only in physics, but in science generally, or maybe you could call it psychology. Mm-hmm. You always have to think about how do I sell my research to get other people to listen to it? How do I get other people to like it? And of course, the easiest way to get other people to like what you're doing is to work on something that they like already.
Yeah.
and that you clearly see this trend that people work on stuff that other people like for sometimes not entirely scientific reasons. Supersymmetry has a reputation of being a particularly pretty theory. It has a lot of aesthetic appeal to it. That's something that you hear physicists who work in these areas talk about very, very frequently. And that's certainly one of the reasons why it attracts so many followers, because people just like working with it.
Can you briefly explain to us what supersymmetry is, please?
Supersymmetry is an extension of the theories that we currently use. We have something that's called the standard model of particle physics, in which we have 25 particles that, for all we currently know, make up all matter in the universe. And in this standard model, we have two different types of particles. They're called fermions and bosons, and they are just different things. Now, supersymmetry is a symmetry that relates the fermions with the bosons so that they actually belong together. Now, the problem is that from the particles that we already have observed that are in the standard model, they do not pair up into the proper supersymmetric pairs. So what you have to do if you believe in supersymmetry is that you just postulate there are new particles to find that pair up with the ones that we have already. And then there's the question, well, where are they? Because we haven't seen them. And the answer to this is that they are so heavy that we have not yet been able to produce them in particle colliders.
Okay. Well, it's from a basic logical standpoint, it does seem a little bit like making the foot fit the shoe as opposed to the other way around. And I guess it sounds like you, for all that physics and physicists have got unbelievably logical brains, there's a lot of probably ego and dogma and patriotism to particular approaches. Do you think that that's restricting physics in moving forwards, this lack of ability to let go of existing models and potentially look elsewhere?
Yes, sure. But I should add that, of course, these ideas do have certain scientific motivations that got them started in the first point.
They're not just plucked out of the air, right?
No, I mean, supersymmetry was something that attracted a lot of attention, for example, because it comes out of string theory. So if you believe in string theory, you actually need supersymmetry. The opposite is not necessarily true. If you have supersymmetry, you don't necessarily also need strings. But since there are a lot of people who like string theory, they are kind of forced to also have the supersymmetry. So that's one thing. But supersymmetry is also something that people like to work with because it solves some mathematical problems with the theories. And that's just something that they find appealing. It's also, it turned out that if you have the supersymmetry and you add R parity to it, then you get particles that can also make up dark matter. So that fit very nicely with the story. But that was, as I said, it was something like 30 years ago. And since then, the situation has just changed, and I think that the appeal of supersymmetry has dramatically fallen since, because we haven't seen it in the data.
Yeah.
But people keep adjusting their models so they become more and more complicated to address the lack of evidence that we have.
Yeah.
And then at some point you come to the question that you ask, like, when do you stop? When do you just conclude that physicists are not able to let go of their ideas because they have invested too much time and effort into it?
Does it feel a little bit like flogging a dead horse sometimes?
I'm sorry, that's an idiom that I don't know.
That's fantastic. So it's
I'm not sure that's so fantastic.
Okay, so it's what it means is you are you've taken every opportunity that you can, you've taken every route that you can to try and distill from one thing something else, and that something else hasn't worked, therefore it's time to move on. It's it's interesting that hasn't crossed over into your vernacular. That's really cool.
I actually once read a whole book with idioms, but I can't recall this. In any case, so that's an interesting question, because if supersymmetry is not the right thing, that it means that physicists have made some wrong decision pretty early on.
Fundamentally.
So we have to go back and ask if one of the assumptions that entered all these arguments that led them to work on supersymmetry to begin with was maybe the wrong path to take.
Wow. So that's potentially an awfully big upheaval in the physics community, I'm going to guess.
Well, you see people discussing this right now. So the argument that I make in my book is that this belief in naturalness is an issue, and that's a problem that needs to be rethought right now. So naturalness is this idea that the theories of physics should only contain numbers without units that are close to one, not much larger than one or not much smaller than one. There are more complicated versions of this, but that's the easy case.
Yeah.
That's something that they use to construct theories. And now it just happens that supersymmetry obeys this idea of naturalness. It actually helps to make the standard model natural. So the standard model by itself is not natural, but if you add supersymmetry to it, it works. And a lot of theoretical physicists take that as strong evidence that there's something true about supersymmetry, that it has power to describe nature. And I just think that that's a wrong conclusion. I see no reason why the theories of nature should have this property that they call naturalness.
Okay, so in your book, Lost in Math, How Beauty Leads Physics Astray, you talk about this desire within the physics community to have beautiful theories. Can you describe what is considered to make a theory beautiful?
Yes. So it's interesting that if you ask theoretical physicists what they mean by beauty, they all more or less say the same thing. So I think this is not an idea of beauty that you find among non-physicists. But for what physicists are concerned, beauty has three major ingredients. The one is simplicity. And by this, I mean that the theory should be simple in absolute terms. I don't mean in relative terms, where you say, well, I take the theory that is simpler than some other theory, but achieves the same. But just that the theory should have simple laws, like it should have unified force, for example, is simpler than for different forces. If you add symmetry to a model that usually combines two different concepts to one or several different concepts, like with supersymmetry, we already talked about this, where you have the fermions and the bosons, they actually belong together. Mm-hmm. So that's a simplification in terms of the axioms of your theory. So simplification is one aspect of beauty. Then there's naturalness. I already told you about naturalness, the thing with the parameters that have no units, that should be of order one.
Yep.
And then the third aspect is something that's usually referred to as elegance, and that's kind of a fluffy criterion.
Very much so. It's not something I expected to hear coming out of physics.
Well, it's something that they talk about a lot. You actually find this also in a lot of older literature. Like there's a book by Chandrasekhar where he goes on about this already. But so what they mean with elegance is that the theory should be simple, but it shouldn't be too simple. So it should lead to some interesting insights. You should have some aha effect here and there. It should have unexpected connections. It should give you some surprises. So that's this idea of elegance. You also find these three aspects in a lot of artworks, by the way. I mean, simplicity is all well and fine, but if it's too simple, it's just boring. Mm. And so I think it's the same sense that you find here.
That's really interesting. It sounds like reducing the theory down to its simplest possible terms is does this cause physicists to look in the wrong places? sometimes when they're trying to develop theories? Is this an artifact of E equals mc squared and other very, very short, very, very simple theories like that?
I would actually say that E equals mc squared is too simple. It's not elegant enough.
That's overshot it. Okay, so that's interesting.
Yeah. But that makes an interesting point, because this sense of what is elegant, what is surprising, what gives you some new insights and so on, depends, of course, on how much you know already. So this sense of what counts as elegant and what counts as beautiful changes throughout the history of science. And you find evidence for this in the literature. When you look back several hundred years, they thought that planets on circular orbits, well, that's a beautiful idea. Also turns out to be wrong. But that's an ideal of beauty that you just wouldn't find today among physicists.
Yep.
It's something that no one would pull upon. Now they have other ideas of beauty, and well, maybe these work or maybe that these don't work. We just don't know. So generally, I think it's a bad idea to impose our current ideals of beauty on the laws of nature, in the sense that we use it to construct new theories. Because the problem is, we were talking about these experiments earlier where they look for dark matter and the particle colliders and, some telescopes and so on and so forth. These are really costly experiments. And we just can't test all theories that theoretical physicists come up with. So we have to make a selection. And of course, we try to select those theories that we consider to be the most promising. Now, if we make a bad choice, we go and test theories that are wrong, then the only thing we get are null results. Now, the null results are also results, of course, but they are not very useful results when you try to develop a new theory. So that gets you stuck in a cycle where looking at the wrong theories gives you null results that gets you stuck at the wrong theories and so on and so forth.
Yeah, well, it's just crossing one thing off the board as opposed to directing you towards the right direction on the board.
Yes, exactly.
Yeah, I mean, it sounds in between the potential for dogma, this dogmatic and patriotic holding on to existing bodies of knowledge or existing directions within the theories, plus this desire for beautiful theories to come out. It must lead to a little bit of an echo chamber and a lot of theories that are similar. And as you say, you add a section onto something which already exists. Now this works despite the experiments not showing anything that supports it.
Yes, that's certainly true. And I think that's an organizational problem with the academic system in general. If you want to get something funded, if you want to get something published, it's much easier if you work on something that people already work on. And of course, people know this, so that's what they do. It's in some sense, it's not particularly surprising. What is surprising is that they accept this and play along with it.
Yeah, I understand. So, where do we go from here? Do you have a suggestion for how physicists can look at the field in a different way?
Well, sure. I think the first step is that they become aware of what they are doing, so that they actually understand where they are using assumptions from beauty that are not scientific. In some cases, I think people know this, but in other cases, I'm pretty sure they don't. Like this idea of naturalness, for example, I would say like half of the people know that it's not a scientific criterion. But the other half thinks it is. So there's clearly something at odds there. Mm-hmm. And there's also this idea, for example, of unification or the theory of everything. I mean, these are all nice ideas, but there isn't really any good logical reason for why there should be a unified force or for why there should be a theory of everything. It's just something that people work on because they like the idea. And so at some point we should draw the conclusion that maybe that's not the right path to work on. And I think it would help if they would just, take into account the arguments for and against it. when they write a paper, say, or give a talk. Unfortunately, it's very common that they only list the arguments that speak for their theory.
Yeah, I can totally see that. You want to hear people. It's a very, very educated version of yes men, isn't it? Having someone who just says yes and agrees with what it is that your particular stance. You've touched on something there that I did want to discuss. There was once upon a time a dream of a theory of everything, or a grand unification theory. Is that a lost cause now? Does it seem to do the current state of theoretical physics suggest that that's not the direction that we're going to end up in?
Who knows? Personally, I think that this whole idea of a theory of everything doesn't make a lot of sense, because, suppose I tell you, here's the theory of everything and it explains everything that we see. How do you know that it will still be a theory of everything tomorrow? Mm-hmm. That we will not at some point measure something that does not fit into this theory. So I think that this is, it just doesn't make a lot of sense conceptually. Then, of course, there is this issue that what people in the foundations of physics mean when they say theory of everything does not actually explain everything. That's just a way to say, well, we have combined all the four known forces into one. So that's what they mean, just to get the terminology sorted out. Yeah. And that might still work out at some point, or it might not. Presently, I think we just really don't know. Personally, I have developed an interest in an approach that is called asymptotically safe gravity. It basically solves the problem that we have with the quantum properties of space and time. But it does not also include a unification of the interactions. You kind of have a framework in which they all fit, but they are not unified in the way that physicists usually speak about unification. But that theory seems to be working just fine. So presently, I don't see any urgent reason for why these forces should be unified. Maybe our universe just has four different forces, and that's that.
Yeah. What are the four forces, please?
Well, one of the forces is gravity. You all know gravity. There's electromagnetism. And then there's the strong and the weak nuclear force.
And the odds are, how much of that has been pulled together? Because there's obviously still conflict between certain areas of that. Have you managed to unify certain areas and others are still out on a limb?
It kind of depends on what you mean by unification. So the electromagnetic and the strong and the weak nuclear force are kind of the same type. Mm-hmm. And we describe them all with the same mathematics, basically, in what we call the standard model of particle physics. But they are not unified in the sense that they are still three separate forces.
Yeah.
And then there's gravity, which is described by a different mathematical framework. So it doesn't really fit together with the other three forces. Usually that doesn't really bother us, because in the circumstances where we use the standard model, so we describe collisions that happen at particle colliders, then we are dealing with elementary particles, and the gravitational force is so weak that we don't have to worry about what to do with gravity. But there are certain circumstances where it would be necessary to take both of these theories into account, like, for example, close to the center of a black hole or something like that. And for these cases, we just don't have a theory.
Right, okay. So to a degree, gravity is the black sheep of the bunch, which is it the most difficult to make fit? You said recently that we've discovered experiments have managed to detect gravitational waves. Is that correct?
Yes, well, that's not so recent. That was in 2015.
Okay, I guess in physics terms, that's a long time ago.
Well, yeah, the prediction dates back, 80 years or something.
Okay, so going back, you'd mentioned there about particle colliders, and the LHC was, during the build-up to it, was hailed as by sensationalist press as something that was going to create a black hole in the middle of Europe. and absorb the entire world, and then it didn't, and then what came out of it was the Higgs boson was detected. But since then, this huge 23-mile round trip experiment doesn't really seem to have elicited much else. Is that correct?
No, that's not correct.
Oh, no.
No, again, as I said, I think you're reading the wrong news. So, probably because you're not a physicist. So the LHC has detected the Higgs boson. That's the news that everyone has heard of. Mm-hmm. But it has also done a lot of other things. It's just that these did not make so big headlines. It has, for example, probed the structure of the proton in much, much better details than was previously known, and found a few surprises there. People are working on it. It has also been able to measure a lot of the constants in the standard model of particle physics to much higher precision than what was previously possible. It has also measured a lot of composite particles that are made of several quarks and measured their properties. So it's not like nothing has been going on besides the Higgs boson. Yep. It's just that the other stuff has not been quite as exciting as producing a tiny black hole that eats up Europe.
Yeah, well, I mean, that would have made the news if it had happened. It would have definitely
if there would have been still news then, yeah.
Yeah, exactly. News in America, perhaps. But I am right in saying that that's the only new particle which it found. That's correct, right?
The only new fundamental particle, yes.
Okay. Is there a likelihood, or are people still holding out hope that it's going to find more? Or again, if we hit a little bit of a glass ceiling with that particular...
Yes, definitely. There are still people who think that supersymmetric particles will eventually show up. So the thing is that this assumption of naturalness that I was talking about earlier would have put the supersymmetric particles in the regime of fairly low energies close by the Higgs, basically. So we should have seen them already.
Okay.
So we know that this idea of naturalness was just wrong, and it's gone out of the window, but nothing has replaced it. And this means that people who work on supersymmetry basically now have no particular reason to think that the particles should be at any particular mass scale. So it could be there in the data, or it could not be there. There are definitely people who think that it will be there, and the LHC has not totally analyzed all the data that they have. They're still collecting data and getting better statistics from which they try to extract more details and so on and so forth. So there's still hope that they will find something new.
But the early evidence would suggest not.
Yes, I mean, so far they haven't found anything besides Higgs.
Okay, so moving on, I wanted to talk about dark matter or dark energy and discuss why that's so important to physicists to find that. Could you explain just why it's such an important concept within physics?
Well, let me start with saying that dark matter and dark energy are totally different things. So dark energy is whatever is causing the accelerated expansion of the universe. That's just a name that we give to it. We've called it dark energy. And personally, I think there's really nothing to explain, because this acceleration of the universe can just be described with a constant. That thing is called the cosmological constant, and you can just go and measure it, and it has a value, and that's it. Mm-hmm. There are people who think that it should have some kind of microscopic explanation. It should be made up of something, basically. And then there is something to explain, but I see no reason for why this should be so.
So the lines drawn underneath dark energy, as far as you're concerned?
Yes, unless you really show me some data that cannot be fitted with that constant.
Okay.
But so far there isn't any, and so far the constant does a good job. So then there's the thing with dark matter. Dark matter is stuff, basically similar to the stuff that we are made of, except that it does not interact with light in any form. So it does not absorb it, it does not emit it, it doesn't scatter it. And it's believed to sit around galaxies, hover around them in clouds, and it plays a big role in the formation of structures in the universe. That's for what the simulations are concerned. Now, the problem with dark matter is that if you believe it's made of a particle, you want to actually measure the particle. And that has not happened. Then the other option is that we actually do not need any additional stuff, but that we should change the law of gravity so that gravity does not work the way that Einstein envisioned it, as with his theory of general relativity, curvature of space-time and the rubber sheet and so on and so forth. But that we need a different theory for gravity, and that's what's called modified gravity. Maybe not the greatest term ever, but that's what it's called. And ever since people came up with this idea of modified gravity, we have had two camps. The one is the big camp, that's the particle dark matter camp. And then there's a smaller camp of modified gravity, and the case still is not settled.
I see. But I'm right in thinking that if it was proven that dark matter didn't exist, I guess it's going to be very difficult to prove that it doesn't exist, because there's always the potential to continue detecting up until the point at which you do detect it. Is that right? Is it difficult to disprove a theory like that? Some people are always going to hold on to the hope that we finally do detect it.
Yeah, so it's basically impossible to rule out, because, as you say, you can always, you build a detector, and the detector has a certain sensitivity to some interaction probability and so on and so forth. And then you can always just say, well, maybe the particle just had a lower probability of interaction than what we have been able to probe so far, so we need to build a bigger detector.
Turn the sensitivity up.
Yeah, right. And that's been going on since the mid-1980s, and the sensitivity has increased by at least a factor 100,000 since.
Oh, my God.
You can continue to play this game as long as you want, as long as you can get money for it. But again, the thing is that the theories that we think are plausible direct the efforts that we make in testing the theories. So if we invest money in building more detectors for dark matter, we cannot invest the same money into, building some telescope and put it on a satellite and measure, gravitational lensing better or what have you, something that would allow us to test modified gravity. So we have decisions to make, and I think we have to be really, really careful as theoretical physicists in how we rate the promise of a theory.
It's very interesting how theoretical physicists and the relative weight behind each of their theories across all of the different subject areas, subdisciplines within physics, is having such an impact on the experimenters and what they get to do and where they can direct their efforts, that you guys are kind of like the roots of the tree, and from that determines what can grow out of it to a degree.
Well, yes, it's interesting, but it's not really surprising, is it? Look, you have a lot of people in a community, and they basically only talk to each other. And they constantly tell each other that what they are doing is interesting and is probably the right thing. Then they believe it's the right thing. And of course, there are a lot of people, they will be able to convince other people that probably what they're doing is the right thing. And then you have this small group of people who work on, just to pick this example, modified gravity or something. There may be a few dozen people who work on this, and they are full of self-doubt. Not so surprisingly, because a huge number of really smart people is working on something else.
The opposite side of the scale, yeah.
Right, and they're constantly saying that modified gravity is a joke. And so the people who work on it are like, they're really, really reluctant to make those big proclamations that the other people have no problem making.
Yeah, it's
so there's just you have this backup, behind your back. You have a large group of people who support you.
Yeah.
That makes a big psychological difference.
Oh, 100%. It must be. I don't know. As someone from the outside looking in, I would. My goal or my aim would be to have to expedite the discovery of whichever theory is correct, not to dogmatically stick to whichever one is most popular. And it seems that it's definitely not for the benefit of physics for anyone who's looking at alternative theories to be ostracized or to, be ridiculed or whatever it might be. Because if that research is the right direction and these people are being reluctant, or someone's in the camp of the existing model of gravity and is thinking that it might not be right, but they're terrified of moving over because of what their peers are going to say to them. That's not a tremendously holistic view or a holistic direction for physics to take overall, is it?
Yeah, well, that's certainly true. The thing is, of course, that if you would go and ask a physicist, they would deny that this is what's going on. Because they are too smart to fall for mistakes like this. And of course, they have good reasons to work on what they work on and so on and so forth. So they think that they are not biased. They cannot possibly be biased by the size of the group that they work on. That's just a possibility that's not on their radar. For the physicists, sociology and psychology are not real sciences. It's not something that they pay attention to. They think it's not necessary.
Which is crazy, because it would appear that an obvious example of groupthink is going on here. You have this echo chamber. You have people that support theories that it would appear have more and more experiments proving nothing to support them, and no one being prepared to move in a different direction. It's so interesting how, as you say, the people that are in the field of physics are so clever, and yet fundamentally appear to perhaps be unable to see the wood for the trees a little bit here.
Yeah, maybe. Well, you say that it's an obvious example for groupthink, but I would be more careful there. I would say there's a possibility that it is groupthink, which cannot be ruled out, because the current organization of the research does not guard scientists for falling for it. There just are no measures against it. It's actually the opposite, that the current organization of research supports this groupthink, because, as I said earlier, it's easier for people to get funding and to get positions if they work in what is already a large group. So I don't really know what's going on. Maybe there's nothing wrong whatsoever. But either way, I think that we should institutionalize some measures that prevent people from falling into this groupthink trap.
That's interesting. So how do you suggest that you institutionalize that?
Well, one of the things I already said briefly previously is that I think that scientists generally, not just physicists, need an awareness for these cognitive and social biases that you develop when you work in large groups. It's just something that people should know of, so that they can recognize what's going on, like this wishful thinking or loss awareness that we already talked about. That's this reluctance to abandon a research project that you have been working on for a long time, just because you have invested a lot of effort into it. There's a long list of these things that, basically you can print them and hand them out to students or something like that. Something really trivial. But then there are other things that have to be done by funding agencies. Basically, we already previously talked about this problem that it's really hard to get out of a research area if you notice that maybe it's not the best thing to work on.
Yeah.
And the major problem is that you have all your expertise in what you have previously worked on. So nobody will give you money to do something else. They will not hire you. You will not get grants. It's just in the current organization, it's not possible. So it's not surprising that people continue to do what they are already doing, because they wouldn't be able to do something else. They wouldn't have money to pay the rent, basically.
Exactly.
And there are simple things that you can do to avoid this problem, by offering people some kind of re-education support. You could say, well, you want to change fields, and there are 1-year scholarships or something in which you will be supported. Maybe not with the greatest pay, but you have 1 year or 2 years or whatever, it depends on the field, of time of learning the basics of a new area. time in which you are not, in which you do not have to produce new results or something like that.
For sure. And do you think that that would allow a more free flowing of talent between different areas and different subdisciplines?
I definitely think so. I can only see positive consequences of this. And there are a few other things that I have noted down in the appendix of my book. But really, the point is that this is something that people in these communities should think about, and they should come up with a list of changes that they want to implement and then just pull it through, or at least try to. So the major problem right now is that no one takes these problems seriously to begin with.
Mm-hmm. Yeah, it's really funny what you said about physicists wouldn't see psychology and sociology as real sciences, and yet it would appear that those are influencing their ability to move forward, perhaps an awful lot more than they actually might think. Their cognitive biases are leading them potentially into, I think you describe it as culdesacs in the book, where they almost can't get themselves out again. We've touched on it a number of times throughout this, where a combination of this echo chamber, and then you're getting backed in by financial restrictions, and also you've got this the weight of the existing rhetoric, the direction of this particular field that you're working within, and all of the social influences that you've got from people in there. It must be a difficult situation for a number of physicists to work in at the moment, who may want to make this move, or who may want to expand their body of knowledge to a different area or an alternative theory, but just feel like they can't do it.
Yes, sure. A lot of them just leave. I've seen people leave. These are people who figure out that they will not be able to get money to work on the research that they think is most promising. And then they just conclude then it's not worth their time. So they just leave academia and do something else. And, there is life outside of academia too.
There is, but it seems like a terrible shame to lose fantastic talent in the field of academia because of this sort of systemic dogma.
Yes, it's a shame, but it's also just a problem for science, because of course the people that are left are the ones who don't have the big problems with joining these large research programs and just producing papers. If they had a large problem with it, then they would be leaving.
Yeah, for sure. But it's not necessarily the best for the subject, the body of knowledge as a whole, right? People could be doing something a lot more productive if it was a little bit more free-flowing.
I think so. This is why I hope that making some organizational changes to academic research would help overcome this impasse.
For sure. So, Sabine, I really appreciate your time. Would you be able to tell the listeners where they can find you online? I'll make sure that I put a link to Lost in Math, How Beauty Leads Physics Astray, your book, in the show notes below. But where can they find you online? I really like your blog, so you need to put that in.
Well, it's not complicated, For all I know, there's only one person with my name. You type it into Google, and the first 100 hits will actually direct you to my websites. I have a website that's called sabinehossenfelder.com. It's not hard to remember if you can remember my name. I have a blog that's called Back Reaction, and that's at blogspot.com. Mm-hmm. And I'm also on Facebook, and I'm on Twitter, and I write for a lot of websites every now and then. So you will find all this by help of Google or your search engine of choice.
Fantastic. Sabine, I really appreciate your time. I hope that we've opened some people's eyes to what the physics community is like at the moment. I hope this doesn't sound like a disparaging criticism of what's going on within there. It's obviously a very difficult subject for everybody to wrap their heads around, even the best minds in the world. But I do think it's so interesting what you've said about these social influences and cognitive biases influencing who we consider to be some of the cleverest people on the planet. And in a weird way, I think it's actually it's a little bit reassuring that for us normal people who perhaps aren't at the level of a theoretical physicist, that they are still subject to these psychological and sociological influences.
Oh my God, you just found out that physicists are humans.
Yeah, I did. Do you know what it is? Sometimes I'm not sure, but I think I did. So thank you very much for your time, Sabine. I'll make sure everything's in the show notes below. Thank you very much.
Thank you. You're welcome.